Hey blockchain visionaries, it's George Levy. In this video, we're going to be talking about Bitcoin mining. And the way that we're going to do that is by actually using 16-sided dice. And actually, when I say dice, I mean a lot of dice. And I'll tell you all about it. Specifically, we're going to focus on proof of work, which is what makes Bitcoin mining possible. It's a very educational session, and I can't wait to share it with you. If you're new to the channel, hit subscribe and hit the bell so you're aware every single time we publish brand new videos. Every single week, we bring you videos on blockchain, Bitcoin, cryptocurrency, and related topics like NFTs, the metaverse, Web3, everything you can find right here in this channel. We look forward to sharing this with you, and today, we're talking Bitcoin mining. Let's do it.
The easiest way to look at proof of work is to actually first look at what we're trying to create. So let me take you right now to a block explorer where we can look at the latest blocks in Bitcoin and what they are. So as you'll see right now, these are the latest blocks that are actually been in Bitcoin. These have been mined. And you can see the miner that relayed this was F2 Pool. Then you have BTC.com. Here you have Huobi Pool. You have Ant Pool. All of these miners around the world are competing against each other to create the next block on the Bitcoin blockchain. Now what you'll notice is that each one of those blocks actually has a block hash. And as you can see, this block hash that each one of them has is a very unique type of block hash because they have a lot of zeros at the beginning. They all consistently have a lot of zeros at the beginning. Now this is where the proof of work comes involved, because in order for F2 Pool to be declared the winner and to officially be able to add their block onto the Bitcoin blockchain, they had to create this block hash for the contents of the block that they made. Now let me take you to a demo blockchain that will actually put this more in context. It's going to be easier than this because right now what you're going to see is there's a lot of zeros here. This is a very difficult block hash to generate. Let me show you exactly what I mean. So right now what I'm taking you to is demoblockchain.org. And in demoblockchain.org you actually have a demo blockchain. For the purposes of this example, what you'll see is that here is a block. A block is composed, it has a number to it, it has a data field, which would be the contents of that block, and it has an associated block hash. As you can see, this block hash has 4 leading zeros. And because of this, you see that the block hash is green. Now, it's green because for the purposes of this demo, a valid block needs to have at least 4 leading zeros. In fact, it's actually a number below a certain target, and that target needs to have at least 4 leading zeros, and it's actually lower than that. What you see as a hash is actually a number, but it has to be below a certain value. So what I'm trying to tell you is that being able to generate this block hash is actually very difficult. Let me explain to you why. Because this block hash, it consists of whatever the contents of this block are. And if I change the block hash, the block contents, for example, let me say that I add another transaction, I have a completely different block hash. You see, the problem here is that you have to generate a hash for the contents of this block. Now, the only way that you can actually generate that hash is by basically changing the contents of this block to be able to generate that hash. So notice one thing, if I try to change the contents of this block, I'm no longer creating the block that I want. Think about the challenge that you have if you're actually the miner relaying this block. Let's look at this block specifically. This block actually consists of, let me take you back to the actual contents of this block, which is here. So if I take you to that block, what you find is that this specific block actually has 2003 transactions. So this miner had to create a block hash that would take into consideration the fact that there are 2003 transactions and each one of those transactions is unique to its own. So the key problem here is that if I am here, if I have, for example, here I have transaction 1, I have transaction 2, transaction 3. Let's say that I were to put 2003 transactions here, right? And this is all the contents of this block. The only way that I could change the block hash for this specific block, well, there's many ways I could do it. I could change the block number, but in this case, that would not apply because this had to be block 662510. So I can't change the block number. I can't change the contents of the block because in this specific case, the miner actually had specifically 2003 transactions, and it has to be those transactions that he's including in that block. Each one of those transactions has been validated. It's a valid Bitcoin transaction, but they are not confirmed until that miner has actually added them onto a block, and that block has gotten added to the Bitcoin blockchain. So how does that miner add that block of transactions to the Bitcoin blockchain? Does that by creating a corresponding block hash for that block. Notice, this is a world battle. There are thousands of other miners around the world that are trying to create their own block. The way that a miner is able to beat all the other miners and to add their unique block onto the Bitcoin blockchain is being able to generate a correct block hash for their own block before anybody else. That's why F2 Pool was able to get these, why BTC.com beat F2 Pool in these, where Huobi Pool came in. It's all a race. Let me show you exactly what that race consists of. If I go back here to this block that I'm generating right now, the only way that I can change that block hash that will not change the contents of the block or the number of the block is to change this field called the nonce. Nonce is usually called a number used once, nonce. So the nonce is a field. It's actually, in this case, it's some numbers that you add into the formula for this block, which the contents will change the hash. Let me explain to you what I mean. If I change the nonce to number 1, you'll see that the hash changed. Let me try number 2. Wait, that one has 1 leading 0, but that's really, really difficult because I need 4 leading zeros. So let me try that again. 3, 4, and I have to keep trying this again and again and again and again and again until hopefully I'll get 4 leading zeros. One way to go about it in this demo is to actually for me to let the computer do it. And what it'll do is again and again and again and again, try different numbers until it gets 4 leading zeros. Okay? Now here's the thing that's interesting that I want to explain to you and why this whole video is here, is the fact that each one of those zeros is corresponding to what would be a hexadecimal field, which has 16 numbers. So let me take you back. If I actually just go, you'll find that each one of these individual numbers, 2, 3, 4, 5, each one of those has a possible 16 different values. Why am I saying that? Because there are the letters A through F, which are 6, and they have the numbers 0 through 9, which is 10 numbers. So when you add 10 plus 6, you get 16. So what we have to do is we have to be able to get a hash that actually has the number 16, one of the numbers, this multiple number of times at once. Let me explain to you by showing you an example by using a 16-sided dice. This is a 16-sided dice, and if I drop it, here I got a number 3. Let's assume that the number for 0 in this case would be 6. So let me throw it. That was 16. Let me try it again. The number is 3. I have to try it again. Okay, that's a 4. So it is very, very difficult to be able to get, in this case, 1 out of 16 numbers, right? So you just have to keep trying again and again. It's the same thing as if I go here in the blockchain demo and I try 1, or I try 2. I'm trying again and again and again. But let's get even more complicated. What if we don't just have 1 out of 16? What if we actually have however many those zeros are? So let's say I have more 16-sided dice. So let's say in this case I want to get 4 zeros. So let's say that the number that we're looking for is, we said actually we want to get the number 4. Okay? So I will have to not only get a number 4 in 1, I have to get a number 4 in the 4 dice at the same time. In this case, well, actually I got 1 4. The other ones didn't, so I have to try again. This is exactly what miners do, but they do it billions and billions of times, and they have to get sometimes 19 zeros at the same time. It's a very complicated process, and the only way that you can do that is by actually doing billions and billions and billions of hashes, one after the other, one after the other. That's why in this case, the example that I have for the demo blockchain only has 4 leading zeros. So yes, I can try manually to try this, or I can let the computer do it, in which case it took 10,906 attempts to be able to find 4 leading zeros. Now, in order for you to be able to get, say, 20 leading zeros, it wouldn't be 10,000 attempts. Sometimes it takes billions and billions of these. And the point is, when these miners are competing against each other, sometimes they're doing billions of hashes per second as they compete against all the other miners around the world in order to get a chance to include their block as a block on the blockchain. Now that we go back to the Bitcoin blockchain, what you find is there's been a new block created. This block was actually relayed by Via BTC. What that means is that Via BTC was able to generate this block hash for their block of transactions, which in this specific case, that block had 2,234 transactions. And all of that, they were able to create a block hash that was low enough to be able to be valid, and they could add it to the Bitcoin blockchain. So the key point that I want to get you out of this whole entire example that I want to show you is that whenever you're thinking about proof of work, that's exactly what you're doing. You have all of these miners competing against each other to try to be able to generate a block that's actually below the value that's required by the Bitcoin network. In this specific case, what you find is that VIA BTC was able to create this block. And he was able, or he or she or the mining group was able to do so many times the hashes with the calculations that they had for the transactions they had, that they were able to have all these leading zeros as the value of their block. I hope this is valuable to you. I found very, very interesting to just think that each one of those zeros that you see there is actually the equivalent of a 16-sided dice. And you have to be able to get all of those specific zeros to match at the same time in the one specific number that you're looking for. So if we were looking, for example, in the number 4, I'd have to keep throwing these dice enough times until each one of those dice, all of them, had the number 4 on them. It's possible. You just have to throw it again and again and again, or billions and billions of times per second, as these miners do whenever they are calculating the next block hash.
I hope you enjoyed this video and that you learned something in the process. I bring you brand new videos every single week, so make sure to subscribe to this channel. And if you have any questions or comments, please leave them below. I would love to hear from you. Until next time, I'm George Levy. We're changing the world, one blockchain at a time. See you next time.